Hi everybody, this is the lesson 4, factors affecting rate. This lesson is very full. There's a lot going on in it, and not all that I agree with, in a way. It's a qualitative look at what kind of factors work against collision theory, is how I kind of think about it. So when we think about a chemical reaction happening, we have to think about it as what are these factors affecting this kinetic energy requirement? So what are going to be some of the factors? So let's just put our little reminder. We need we need a collision. So these are the factors of collision theory. 2, sufficient Ke. And 3, we need sufficient Ke. And the last one, and orientation. So these are our 3 factors of collision theory. TRA. So the things that are going to affect this. Step 1, the nature of the reactants, the types of bonds that are being broken. This essentially is going to affect that second requirement. So this nature of reactants, and this affects, or maybe I'm going to put this down here. Yeah, bonds breaking. This affects the Ke requirement. So this affects the Ke requirement of our collision. So bond types, compound types, those are all going to impact bond strength, and then that impacts the rate of reaction by impacting how much kinetic energy you have. Remember that because of the kinetic energy distribution, the Boltzmann distribution, check that out. Boltzmann distribution sounds better. Yeah, the Boltzmann distribution. Well, there's an error in my last video. I'm doing a search right here. Kinetic energy. It's for sure Boltzmann distribution. Okay. The Maxwell-Boltzmann distribution. Ah, boy. Well, who is Bozeman? Bozeman's the other chemistry teacher out there. So because of the Boltzmann distribution, that's this thing that I just finished talking about in my last video. This is the number, and this is kinetic energy. Because of this distribution, the easier a chemical reaction is to happen, the weaker the bonds, the faster it will be, because more particles will be above that kinetic energy requirement. That's really the key. So, this is a good way of sort of comparing 2 chemical reactions and kind of debating about which one would be faster at a given temperature. So if the chemicals have really strong bonds, like ionic bonds, salts typically need to be at very high temperatures to react, unless there's some other factors at play. If a chemical reaction has covalent bonds even, you probably are going to have to increase the energy to do something with that. So compare, for example, let's look at like iodine. So pure iodine is a rock. It's a silvery metal rock, and that metal rock is mostly made of covalent bonds between 2 iodines. So the iodines themselves are very tightly bonded, and then each of those iodines is van der Waals force attracts them to each other. So you have a whole layers and layers of iodine. It forms a relatively, it's not the strongest metal in the world. It's not even really a metal. Iodine metal. It looks like little crumbly bits of rock. You can probably crush it at home under like a piece of glass or something, and it starts to boil at 184 degrees Celsius. That's pretty low, right? Like if I have a plastic plastics generally will melt at sort of 200 degrees Celsius. So like a good thermoplastics, usually about 200 degrees Celsius is where it really starts to flow. Now, the other thing about iodine, as soon as it starts to break down, it turns into a gas. So there's a lot of sort of factors there that iodine, it has covalent bonds in it, but it also has van der Waals bonding. So it's a pretty complicated concept, but in general, if you have some chemical that's fairly straightforward, like sodium chloride, and it's ionic, and you're expecting sodium chloride to react at room temperature from the solid state with something else, you're probably going to have to put in a lot of energy before that sodium chloride is going to be at a reacting level. Now, if you could convert that sodium chloride into a more reactive form, maybe engage it in some hydrogen bonding by dissolving the sodium chloride, well, then you would put it into a state that was more reactive, because the ionic bonding would be already overcome by a different interaction, which would be the dissolving part. So we have to watch out that the aqueous phase does mess things up a little bit. So that's one of the reasons that in my next reaction I did not like that there was a aqueous part to it. I think that convolutes everything. If you wanted to get hydrogen gas and iodine to react with each other versus lead nitrate and sodium iodide, if the sodium iodide and the lead nitrate were both in the solid phase, and so we're trying to talk about these in the same type of phase, we would have to put in a lot of energy so that we could melt that lead nitrate so that it could be in a phase that would actually react with the sodium iodide. Because in the solid phase, that reaction is going to be very slow. There are things like these, like there are examples of solid-solid interactions or reactions that you can do, where you probably could take these two rocks, put them in an oven, heat it to, my gut guess is like 500 degrees, crush both salts up, raise it to 500 degrees, maybe 700 degrees, and leave it there for a week. And if you did that, you probably would form a bunch of lead iodide and a bunch of sodium nitrate. Comparatively, if I wanted to make hydrogen iodide from hydrogen gas and iodine, I probably only have to put in like 200 degrees Celsius to cause that chemical reaction to start happening. Maybe like a match. Probably with a match, I could probably do this hydrogen iodine reaction. And it would happen almost instantaneously. It'd be very, very quick. This lead iodine reaction, even at the same temperature, even if we assume that the match is like 700 degrees, at the same temperature we would have a much slower process, because you're essentially waiting for that little tip of the Boltzmann distribution. We essentially are going to have two reactions here. We that both have the same distribution. Reaction 1 is down here, right? The activation energy of 1 is here, and the activation energy of 2, oh, that's being like very generous. Activation energy of number 2 is over here. So this is my reaction energy 2, and this is my reaction energy 1. So that would be my prediction. That's sort of where I would see. That's how I would sort of compare these. So in both cases, you could have them at the same temperature, the same energy, the same distribution of atoms, but the activation energy is going to be much lower because the bonds that you need to break is much, much weaker. Now, if you had a bunch of chemical bonds that you needed to break compared to a few chemical bonds to break, then the reaction would proceed slower for the one with the more bonds. So we should always assume that chemical reactions occur in steps of one bond breaking, maybe one bond forming at the same time. There are the occasional exceptions, of course, as there always are in chemistry. But at a first assumptive glance, this would be a good presumption to make. And so when we compare two chemical reactions, we could say that that this first reaction here, where there are only bonds between nitrogen and oxygen and between two oxygens, so whatever that is, maybe it's 4 bonds or something, compared to the 8 or more bonds and the 25 O2 bonds that we need to break, it will take much, much longer in terms of a kinetics reasoning, for example, 2. So one way to think about this is probably best thought of as playing upon the rule, upon the requirement of correct orientation. So it plays upon requirement for both collision and correct orientation. So so the more bonds you have, the more correct orientations that you must satisfy. More bonds equals need for more collisions with correct orientation. No, go back. Orientation. Okay. That looks like it's getting kind of small, so I'll try to convert that. Convert to text. Plays upon the requirement for both collisions and correct orientation. That's what I wanted to say. It's a little bit tiny. Let's pump that up a little bit, and there we go. Oh yeah, well that's pretty much exactly what I said at the bottom here. Okay, so if the reactions have similar bonds and similar number of bonds, then the state of the reactions is important. And this is also going to play on some other factors. So I think that I got off on the wrong tangent here in my explanation here, but state has the most impact on how many collisions are possible in high energy states, plasma, gas, liquid. The number of collisions, the number of collisions is higher. Collisions will be higher, and the number of possible orientations is higher. Okay, so we have in gases, for sure, we have the complete freedom of motion, freedom of orientation. So this is what's called degrees of freedom. We have the most ways that the particles can interact and bounce off of each other, and in that way they have the highest chance of colliding with one another. And so in general, for similar reactions with similar concentration, reactions in the higher energy phases will react faster. Now, temperature changes, these also will have a high effect because they will impact the kinetic energy requirement. So this is I want to make a text box over here, just a text box. Impacts kinetic energy requirement. So the more kinetic energy you put in the system, the more particles have the correct amount of kinetic energy. So if I draw an activation energy barrier here, and I say this is EA, then notice that this one has way more ready to react. Way more can react. And at the lower temperature, less can react. Barely any of them have enough energy to react. And if they are not close or they fail to reach the correct orientation, then they will not react either. I guess that's what was supposed to be done on this picture here. So you can see that the increase in particles possessing the amount of activation energy. More kinetic energy in the system, the more particles that satisfy the kinetic energy requirements of the collision. Also, a higher rate of collisions per second. Probably per like speed of light almost. Not speed of light, but so concentration, this is another one. This is really just satisfying the it really affects the requirement for collision. So it affects first the requirement for a collision for reactions. If there are not sufficient concentration, then reaction dependent. Then reaction is unlikely, or then collision is unlikely. And then the more you have, the more likely the more collisions you have. So the more collisions you have, more collisions equals more collisions with the correct orientation. I believe in the stream I mentioned how, you know, we really like drug dosing really depends on this rule. Typically what you're doing when you're getting, if you are getting dosed with, when you get an order of drugs at the pharmacy, you'll get it for a couple of weeks. One of the tricks that you're trying to do on your body is you're trying to keep the concentration level of the drug in your body high enough that the chance of it colliding with the target site, whatever that is, if it's an antibiotic, the chance of it targeting with the antibiotic or with the bacteria, or if it's a whatever, if it's if it's a pain medicine or whatever, the chance of it targeting the correct protein, the chance of it colliding with them has to be kept at a certain rate by and that will be by using keeping the concentration level high enough. So that's really what we're trying to do in those examples. Higher concentration, faster reaction. The other option is a catalyst. A catalyst is a substance that will speed up a chemical reaction by reducing the energy requirement. So this is playing on effects or targets the kinetic energy requirement of our collision theory by reducing this requirement. On our Boltzmann distribution, this means that we're shifting the arrow back, right? So here's my example here. The collision with the catalyst, we are reducing the energy requirement, and so by reducing the energy requirement, we open up the ability for many more particles to react. Now, there is an opposite that I did not mention previously, but there is something called a inhibitor. Inhibitors are catalysts, are similar to catalysts, only they increase the activation, the EA of a chemical reaction by interfering with the chemical pathway. This can be, so inhibitors can be useful in some cases. Sometimes an enzyme reaction, for example, is happening in a way that is unfavorable, or it's not something that you want it to happen. It could also be valuable for slowing a chemical reaction. So they're useful for slowing a chemical process or stopping a chemical process from happening at all. Now, pressure changes is a funny one. Pressure changes are really just playing on the concentration requirement. This is pressure changes equals concentration changes. So it's all the same logic. It's just that in the case of gases, we can affect, instead of having to always add more product, we simply can just decrease the volume or find ways to increase the pressure in there, and that will increase the chemical rate. So higher pressure equals higher rates of correct orientation collisions. All right, so hopefully those are all very obvious to us. The last one is the surface area. Surface area is going to be a factor of the correct orientation. Correct, so this is a correct orientation factor, mostly. Increased surface area opens up more possible orientations for reaction. This is one of the biggest problems in biochemistry, is that biochemical molecules are huge, relatively speaking, and these huge biochemical molecules typically have essentially a lower surface area, and the reactive site is actually usually very, very small. So when we think about an enzyme, typically we are drawing something that looks sort of like this, and then there'll be some sort of little tiny gap in there, and your molecule, whatever it looks like, has to, so this is our, what do we call, substrate, and this is our enzyme. This substrate must go in exactly this specific area. It must enter in a specific target site. So this is what we call, in biochemistry, call this an active site. And if it doesn't get inside that active site, then it doesn't react. And so this is one of the ways that enzymes can be slowed down. Or one of the reasons that enzyme reactions can be slow to initially start. The rate determining step of a biochemical reaction is simply just getting your chemical inside of the enzyme. And then once it's in the enzyme, the chemical reaction happens very, very quickly. The last one that I mentioned in class was mechanical action, which is not mentioned here. So mechanical action is another way of increasing the number of effective collisions by making the system more disordered. And so that simply means taking like a stir stick or a stir bar and actually stirring the chemical mixture up. This process will increase the number of ways that the chemicals can interact and the chance of them interacting as well. So let's do a little bit of practice before we end this video. In general, what effect does an increase in concentration of the reactants have on the rate of reaction? So I'll type this one. So increased concentration equals increased rate. More particles means more chances for particles to collide, and more chances for those collisions to have correct orientation and energy. So one thing to think about for the future, especially as I'm making these videos after we finish this unit, one thing to think about is that if you start to remove reactant by actually completing these reactions, then when you remove those reactants from the system by forming product, you will slow the reaction down because those reactants are no longer there to interact. Those reactants are no longer there to react and to interact with your product. How do changes each of the following factors affect rate of a chemical reactions? Changes to each of the following factors. So use diagrams. Oh boy, lots of work here. Okay, so temperature increased T equals increased rate. More particles will cross the activation energy threshold. And that is from our Boltzmann distribution. I'm going to say that a million times now just so I get that right now. So we have this distribution and then we have this one. This is high T, activation energy, EA, so high T equals faster. Okay, particle size. Smaller particles have increased surface area and more possible correct orientations for reaction. So this can be thought of as one of the reasons why something like propane, which is a 3-carbon molecule, compared to, say, butane. Butane may burn, I believe butane burns more energetically, but propane probably has a lower ignition point. So we use propane in our barbecues because we don't really want that much. We don't need our barbecues to get that hot. And then a butane lighter can actually be used to light a propane torch in that way, I guess. Maybe that makes sense. Someone can correct me another time. Increased pressure increases the number of chemical collisions. Which equations of the following pairs of equations would occur fastest under the same conditions? Explain your answer. So in this case, this is a change in phase. And I don't remember, I feel like I've skipped over the aqueous thing. Where is concentration? Reactions, similar bonds. Then the state of, state of reactions. I see, I did skip one piece here. This is important. I hope you waited till the end of this video so that you could catch this important addition here. So an important addition is the inclusion. I'm gonna put this in bold, I guess. Bold, and let's put it in bright red. Okay. Special aqueous reactions are much faster than solid reactions because the reactants are much more mobile. I guess it's not that huge a reveal. So in the aqueous system, which is common for salts, we're going to get a much faster reaction because the particles are already separated and now the entire atom is exposed. So in the case of the zinc here, we would have essentially a sort of a bar of zinc where all the particles are sort of trapped inside in lines. You know, the sulfur will be a little different. It's sort of going to be in some sort of powder form. But in the aqueous system, you can have a container where the atoms of zinc and the atoms of sulfur, are completely separated already and already ready to react. So let's go back down size here. Bold. Okay, aqueous systems are much faster than solid, even if the product formed is the same, because the particles are much more mobile and separated. Easier to collide with correct orientation. Okay, so in this next reaction, we have an aqueous example of a peroxide breaking down versus a solid and an ionic bond. So I think the example they're going for here was a comparison of bond type. I kind of disagree, but I suppose that peroxide breaking down is elephant toothpaste, which is a pretty violent reaction compared to the copper tree or the silver tree, which they didn't do correctly at all. So that's funny. Another edit for the book here. This is actually the formation of solid silver. Okay. Gonna have to work that section over. Okay, so in this case I'm gonna type it. So the peroxide should be faster because the bond breaking is a covalent bond compared to the strong metallic bonds in copper. I think that we can almost ignore the silver nitrate bonds because those are already in the aqueous phase. So the AgNO3 is already in the aqueous phase, so its bonds are already somewhat are broken. That's a little bit of a challenging extra concept. I would never ding you on points or anything there, but if you want to know the reason there, when we say the term aqueous, we're actually implying that the atoms have been separated by the water. So the two salt components there, the silver and the nitrate, are already separated. And so really we're just waiting for the copper to break away from its metal piece to interact. All right, we got another example here. We have an aqueous system, lead nitrate and potassium iodide reacting with carbon and oxygen. To me, this is an uncomparable reaction. We have so many differences. We've got a difference in phase. We have a difference in bonding. I think this is just a bad question. So bad question. If I had to guess, the gas phase is the faster reaction because phase is faster reaction because atoms in the gas phase are more kinetically active, but aqueous reactions are also very quick and the bonds being formed are very strong. So unclear. How about that? Do you like that reaction, that answer? This is one. This is one of the ones I did not do on the stream because I knew it could produce some interesting answers. Here we got another one that's really weird. I'm going to guess that the nitrate is faster because we are in, so here we have similar phases, but the number of bonds is lower for an O reaction, and the iron has high energy metallic bonds. So reaction 2 is faster. Let's see, but could we compare these ones better? Could I think about this? I've got ionic bonds in the first one, covalent bonds in the second one. I have a lot more bonds in the second reaction for C. So I'm just looking back at C, see if they had a secret answer that I'm not thinking of when they thought of this question. Okay, we have 2 ionic bonds. So we got 2 ionic bonds. I guess 4 ionic bonds in total. 4 ionic bonds. Here we have 3 and 5. We got a bunch, let's just call it a bunch, of covalent bonds. So we did say in the earlier instructions that if we had to compare, we should, if we read the notes carefully, they do say that we should always go by bonds first. So bond type first, bond type first. So this is the faster. And then we should compare phases later. So let's just write a little cheat sheet here. Based on our notes, we want to compare bond type first. Then, if they are same, then number of bonds. And then, if you have to keep going, then compare phase. And then phase of reactants. So how about that? So here we would say we compare these two. This one's covalent, metallic, and also we have less bonds. So this one is faster. The previous question, we have ionic and covalent. Even if it's aqueous and gas, we're going to start by comparing the bond type first. So this is going to be the answer. So the faster. Comparing number B, we've got ionic down here, and we've got covalent. So we should say covalent. So that's the faster one. Here we have the same type of bond, right? Both are ionic. Both ionic. Same number of bonds. So then it goes to phase. Phase determines. There we go. I knew there was a rule. I should have read those through, I guess, but that's okay. All right, next time we talk, we'll talk about reaction mechanisms, probably tomorrow, I guess. All right, have a great day.